Alright guys, here's the first video for the fall final review. We're coming to an end here. We only have 1 week to review, so let's go ahead and recap the first things we learned this semester in the beginning of September, end of August, beginning of September. The very first units, hopefully the latest units here, 4 and 5 will still be fresh in your mind. But let's go back and recap a lot of the things we forgot from the first few units. If I need more videos, we'll make more. But let's start with the latest, the very first units that we learned this semester. Okay, so I gave you in class. I gave you this little formula sheet over here. You cannot use formulas on the test, of course, but this is a good summary of everything we learned so far. So the very first thing we learned was reviewing lines, linear functions, and absolute value, linear absolute value. Those things we learned in Math 1. So as you can see here, this whole semester we learned 6 very important functions. Linears, absolute value, quadratics, exponential, rationals, and radicals. Okay, those are the 6 functions we learned. And they all have a lot of things in common. So for example, let's start with linear here. The form of a function, okay, the transformation of functions, they have characteristics that are the same. They always have this h and this k. This h value is a horizontal shift that we do to the function. We grab the parent function and we shift it left and right. The k value is a vertical shift. We grab the parent function and we move it vertically up and down the y-axis. So get used to being able to identify h and k is what we practice all semester long. Most of my students are not used to seeing the k on this side. Some of the students, they're used to seeing it both ways. I can also add the k to the other side, and I can get a similar form of a function here. Y equals m parenthesis x minus h plus a k. Okay, so the students in my class are most used to this form, but either way you should be able to see that the k just got moved to the right side of the equation, and here's on the left side of the equation. Okay, so either way. If we keep it consistently on the right side of the equation, we say often opposite of h and same as k. Okay, so if you keep it that way, then you can always do opposite same to identify the starting point. And these are some key ideas. The linears, lines goes forever, so the domain goes from negative infinity to positive infinity, and range goes from negative infinity to positive infinity, because lines goes forever and ever and ever, they never end. The domain in every single function, we always read it from left to right, and the range we always read it from bottom to top. So always, as you can see, is written the same pattern all throughout every single function. So get used to either seeing the k on the left or the k on the right, and then if it is on the right, is opposite same. Of course, if it is on the left, it would be opposite opposite. So pick one way and get used to it. All right. So we should immediately be able to graph y equals x line. Okay, the same value I pick for x, it will correspond to the y of value. So this line is a 1 for x, 1 for y, 2, 3, the pattern is the same here. If I pick negative 1 for x, is negative 1 for y. This is a classical, very classical function here. And here is the function of this parent function, y equals x line, right there. Okay? As you can see, there is no h and k here on the parent function, so that means it's 0, 0. We started at 0, 0. And the slope, which is the number right in the front, is up 1, run 1, up 1, run 1. So you can either plug in points or you can identify the h and k and the slope. So m stands for slope. And you can see, as you can see here, lines have slope and linear absolute value have slopes. The other functions do not have m written on it. They have an a. That means a stands for a stretch, and that's what the word we use for quadratics, exponentials, rationals, and radicals. We use a, are stretches. They don't behave, the a does not behave the same as a slope. Okay, slope is rise over run and is constant. is a constant rate of change. Stays the same, up 1 over 1, up 1 over 1, up 1 over 1, and it keeps on going, up 1 over 1. And the absolute value is the same as well. The other functions do not behave in a constant rate of change. All right? Let's talk about absolute value now. The absolute value behaves exactly the same as the linear, but the absolute value of any number is never negative, so it is always positive. The absolute value of negative 10 is 10. The absolute value of negative 5 is 5. So it's a positive. There's always a positive answer for absolute value. The h and k is going to be the same. We may rewrite this as y equals m. That means I have a slope. Absolute value of x minus h, and I can add my k to the right side of the equation here, and I can go ahead and identify as opposite and same. Every time I see an absolute value, I think of the v shape, okay, because that's what it is. It's a v-shaped function. So if I look at the parent function, I can see the h. There's no movement, there's no horizontal movement, there's no h being added or subtracted to x, and there is no k. So that would be 0, 0. And then I look in front of the absolute value, just like my function says here, and I look for a slope. And there's an invisible number 1. So I go up 1, run 1, up 1, run 1 to the right, and I do the same thing to the left. Okay, it is not a line, it's not going down, because the absolute value of negative 1 is 1. The absolute value of negative 2 is positive 2. The absolute value of negative 5 will be positive 5. That's why it behaves in a V-shape line. In a V shape, okay? So there is our absolute values. Every single absolute value will have a V shape because of absolute value is representing distance, and distances are positive. There's no such a thing as negative distance. So the domain is from left to right and from bottom to top. So if I was to say the domain of my my function here is from negative infinity, because we're coming here from negative infinity all the way to positive infinity on the x-axis. So every single point here in negative 10, the absolute value is a positive 10. So I can take the absolute value of any number from negative infinity all the way to positive infinity. That's our domain. The range is from k value to positive infinity, or from negative infinity to the k value. It depends if the v opens up or if the v opens down. So since my v opens up, my k value is 0, and my v is going towards positive infinity in the y-axis. So my range here would be, my domain here would be from negative infinity to positive infinity, but my range would be from 0, including 0, up to positive infinity. Okay? So that is my range for this simple parent function right here. And then let's talk about quadratic. When I think of quadratic, x squared, I think of parabolas. It's a nice smooth curve, not sharp like the v up here. The absolute value is a smooth curve. I also be careful because now I'm no longer dealing with slopes, I'm dealing with stretch. So I like to put a nice separation here. Now things get different, okay? I'm dealing from the bottom down, I'm dealing with a stretch, not with a slope. So I cannot count up 2, run 1, or up 1, run 1, all the way through. That's not how it works here, okay? You gotta be careful. So again, there's a specific characteristic for quadratics. It has a square to it. That's what quadratics are squared functions, quadratic functions. Sometimes the students will see, and here's a mistake that happens, they will see a linear function. Take a look at it. A linear function, they say, oh, that's a quadratic. It's not. Where is my square value? Where's my power of 2? It's not here. So that's not a quadratic. It's a linear. They look the same, but a quadratic has a power of 2. So that's what you need to look for to know it's a quadratic. Okay? It behaves very similar to the other functions here. We can add the k. It will be y equals a, which is my stretch, x minus h squared plus k, and I can call it opposite of h and same as k, just like I'm going to do to every single function here in my, my paper here. All right, take a look at the ideas about domain and range from left to right, from bottom to top. Is the same throughout all of them. Let's go ahead and take a look here. A parent function, I'm not adding or subtracting any h value. I'm not adding or subtracting any k value. Parent functions always has the vertex as 0, 0. And the value in front of it is an invisible 1. So I go up 1 and over 1 to the right and to the left. And I draw my nice curve that goes up. Okay. If in front of it I had a negative 1, I would be going down here. And it would be a reflection. It would be a negative parabola. But this is a positive one, is our simple parent function. Okay, so take a look. Negative infinity here on the x-axis all the way to positive infinity. I can take the square root of negative 100 and I'll get a point up, and my parabola is pointing up, saying it's going up forever. Okay, so my domain is negative infinity to positive infinity. And my range is from the k value up to positive infinity, because I am opening to the up positive infinity. So it would be from 0 to positive infinity. That would be my range. If I was opening down, would be from negative infinity up to my k value, from bottom to top. Right, now let's review exponentials a little bit. Things starts getting a little bit different from one to the other. Each one of these last four has something special about each of them. Exponential, I remember something very important. We have an asymptote. Okay, there's one asymptote. Maybe you need to write one asymptote, because on rationals we have two asymptotes. Maybe you need to remember that. Okay, so those are important little hints. Each one has a special characteristic. In an exponential, I remember we have an asymptote, and that is marked by our h and k. I'm going to move the k to the other side. A is our base number, x minus h, and then I add the k here outside. Some people like to put the h and k in parentheses. I'm okay with that. So there we go. Our a is our base number. So let me write something different. Let me write y equals 2 to the x power. That's probably what you're going to see most often here. Or y equals 3 to the x power. Those are the most classical exponential functions. So h and k marks our asymptote. So let's make a note here. H and k marks the asymptote. And then the a value is our stretch. So maybe you need to make notes, important notes for every single one of them. Okay, h and k marks our asymptote, and that's going to be our very first thing we want to mark on the graph. If I look at 2 to the x power, the x is not being added or subtracted the h value, so that's going to be a 0. And there is no k, that's also 0. So the vertex is 0, 0 here. Not vertex, but asymptote. Okay, the starting point. So here is our asymptote. We only have one for exponential. And the stretch, let's use only the 2 here. I'm going to, from the vertex, I'm sorry, before I mark that, that 2, my very second point is directly above h and k. Okay, that's my second point. So my very second point here, which is the first point on the graph, is directly above the h and k. And the third point is our stretch. Okay, now let's go ahead and from the vertex count 2, up 1, 2, over 1. And there you go. So there's 3 things I mark. The vertex, the asymptote first with h and k. The point above the vertex, or the h and k, the open circle here, and then I count the stretch. And then we make this nice curve, and that is our exponential. If you want to investigate a little bit more, create a table. Plug in 0 for x, 1 for x, 2 for x, and then plug in field values so you can see and remember how to graph this. So we always want h and k to mark our asymptote, and then we want the point directly above the h and k value. That's the very first point on our graph. but our asymptote is very important for our graph as well. And then the third point is our stretch. Positive 2, then I go up 2 from the vertex. So like A from the vertex, okay? That's how you do a exponential function. Now, exponential functions never touch the asymptote. So we count from left to right. So it's negative infinity to positive infinity. But the range never touched the asymptote, so we are not going to use brackets. As you can see here, the range is from k to positive infinity or from negative infinity to k. In this case, it's an increasing function, so it's going to be from my k value, which happens to be 0 to positive infinity. We don't touch 0, that's why we don't include with brackets. All right, another important one we just learned in Unit 4. Unit 4 is rational functions. So that is the two most recent right here. The rational functions, I can rewrite this with the k on the other side. Y equals a all over x minus h plus k. And then we're also going to do opposite of h, same as k. The domain is from left to right. We have a nice little pattern for the domain, a nice little pattern for the range, and this function has two pieces, okay, and both pieces are important. It has two asymptotes. The h and k marks our vertical and the horizontal asymptote, okay? In this case, h is 0, k is 0. So this is the 0, 0 value. I mark the horizontal and the vertical asymptote. And then the very second thing is I use my stretch. The first is the h and k. The very second thing is the stretch, okay? Whatever the stretch is our a value, right? So since this one is a 1 from the vertex, I go up 1, run 1. But I also got to do the other side over here, which is down 1 over 1. And I know it's a curve that never touches the asymptote. So it's a nice little curve that goes forever, okay? And here we go, a nice curve that goes forever on both directions. And if you want to plug in a few values, this is always going to be a fraction, okay? The only whole number that you're going to get is if you plug in a 1. 1 for x, and you get a 1 for y. If you plug in a negative 1 for x, you're going to get a negative 1 for y. Those are the only whole number values that we're going to get. Anything else that you plug in, a 3, you get a 1/3. If you plug in a 10, you get a 1/10. That's why these functions get really, really, really close to the asymptote. It gets smaller and smaller, but does not ever become 0, okay? Because we cannot have 0 in the denominator. All right, our last function, which is Unit 5, we just finished Unit 5. It is our radical functions. In radical functions, we have the h and k again. I'm going to move it to the other side. A times the radical of x minus h plus k on the outside. I'm going to use opposite, opposite. So that marks our very first point. So our very first point is our h comma k. Our second point is the stretch. And our third point has a special pattern of moving 4 to the right and up or down to a. Okay, so that is a special pattern. So let's go ahead and graph the parent function. The vertex here is 0, 0. And then the stretch in the front is a 1. So I'm going to go up 1, run 1. And then I come back to the vertex. I move over 4. 1, 2. Can't see this, but 1, 2, 3, 4. And 2 times a. Well, 2 times 1 is 2, so we go up 1, 2. And there is a nice little curve for our radical function. So there we go. And then you can see the domain here. We do not put any values negative inside of the radical because that would be imaginary. So that means my domain is from 0 to positive infinity. And my range is from k to positive infinity, or if I am decreasing function, would be from negative infinity up to that k value. And that pretty much summarizes all of our 5 functions 6 functions that we learned this year, okay? This semester so far. So they have a lot of things in common, a few different things about each of them, specific things. So review this, use this as you are creating a lot of your, doing a lot of your problems. I will do a few graphing here on your worksheet, okay? I'm going to keep that on the next. There's a lot of rules to remember, so that's why you got to do lots of practice here with your packet. Let's go ahead here to a few of these functions right here for us to play with. Number 5, let's start with that. Take a look at number 5, and the first thing you should do is identify what kind of function do we have here. I have a parenthesis, -1 plus a 2 outside. I don't have a square, so that is not a quadratic. I don't have an absolute value. This is not exponential. Definitely not radical, and definitely not rational. This is a line, okay? So for a line, we just need our starting point, which is opposite of h, which is 1, same as k, which is 2, and I'm going to go to 1, comma 2. There we go. Because it is a line, we do have a slope, and the slope is up to run 3. So up to run 3, there is our 2 points, just enough to draw our lines. Lines are the easiest. If you want to add another point, I went up 2, ran 3. I got to do the opposite. Drop 2 and run 3 to the left. I would have 3 points on the same pattern here. You can go ahead and draw your line. All right. So, and then it says accurately graph the given equation on a separate sheet of paper or here and state the domain and the range. Linear functions goes forever. That's why I put an arrow on the left and on the right. So the domain would be from -infinity to +infinity. The range would also be from -infinity to +infinity. Okay? Take a look at the other one. That's why I like 5 and 6 right next to each other. They look almost exactly the same. Visually, they look almost exactly the same. But it has, number 6 has a square. That is a parabola. I know I'm supposed to do some curvy U-shape graph. So I can use my vertex, opposite and same. So opposite of h is 1, same as k is 2. So I'm going to 1, comma 2. 1 for x, 2 for y, right there. But this is not a rise over run. This is not a slope. This is a stretch. A stretch of a is -1/2. So I'm dropping 1/2 from my vertex, drop half of it, and go 1 to the right and 1 to the left, because parabolas are symmetric. The same thing you do to the right, you do to the left. And then you can connect these points. It's a nice little parabola that points down. We know it points down because it's negative. And I only went half. That's all they're asking me, to go halfway down, 1 to the right, 1 to the left. Okay, put your arrows pointing down. So we know the domain is going to be from -infinity all the way to +infinity, but the range is from bottom to the top. Okay, so I'm coming from -infinity all the way up to a 2. So I'll let you write the domain and range of these functions so you can play with it. Now let's take a look at number 7. Number 7, something gives it away. The absolute value bars tells me this is an absolute value function. Is the V shape. The 2 is written in the front. That's the K value. It should be written back here. So if you would like to see it visually written in the right form, would be Y equals the 2. I'm going to write it in the back, so I'm going to skip it for now. The negative is my slope in front of the absolute value of x plus 4, and I'm just going to write the 2, positive 2 in the back. I am not subtracting the 2 across the equal sign. Okay, I'm not subtracting to the other sign. I'm just rewriting it on the back portion of the absolute value. Okay, so there we go. Now you can see that the opposite of 4 is -4, same as 2, it's 2. So let's go to -4, -1, -2, -3, -4, up to 1, 2. This is my starting point. I'm supposed to do a V shape. Sometimes the V shape opens up, sometimes the V shape opens down. Let's take a look at the slope. The slope is the number right in front of the absolute value, and we have a -1. -1. So I know I need to drop 1 and run 1 to the right and run 1 to the left, because a V is like a U. They're symmetrical. So there we go. I open up my absolute value. I open my absolute value here down, not up. Open down my absolute value, and there we go. It looks like I'm going to go on forever. That's why I put my arrows. So my domain is going to be from -infinity all the way to +infinity. You can keep on going and going, plugging in high values for x, and you can also plug in negative values for x inside of our absolute value. That's why our domain is from -infinity to +infinity. But our range, we read it from bottom to top. So it would be from -infinity all the way up to a 2. That's where our y value would stop, is at a 2. So you can do your domain and range. Now let's take a look of, we did a line, we did a quadratic, we did an absolute value. Let's do an exponential here. Okay? An exponential, we look at h and k. H is the value being done to x. I see a -1, so the opposite of -1 is 1. I don't have a k value, so that's 0. Okay? At 1, 0, in exponentials, we have one asymptote. That marks our asymptote. So at 1 for x, 0 for y, right here, I'm going to mark my asymptote within this open circle. It's very important, the open circle. The point right above it is my very first point of the graph. I guarantee you, if you plug in a 1 for x, you will get a 1 for y, because 1 for x would say 1 minus 1, which is 0, and 2 to the 0 is 1. So you would get this point right here, 1, 1. Now come back to the vertex and count the base, which is 2. From the vertex, count up 1, 2 over 1. And there's our second point, which is the second point on the graph. So I know it's a curve that does not touch the asymptote and is increasing up forever. So there we go. That's our exponential. My domain, I know I'm coming from -infinity all the way to +infinity. And my range is going to come from my range, I'm coming from the asymptote up to +infinity. Does not include the asymptote. Take a look at your little formula sheet so you can see. Okay? So that gives you an idea of this 4. There's more for us to graph. Over here, number 9 and 10, you have another absolute value on 10. These are restricted domain functions. You graph it exactly how you would be graphing it, but then you have to shave it off. Like I said that, shave it off, because you only want it from -1 to +2. So your graph, you can graph it, but then you need to come and erase it, because you only want it from -1 to +2. You want it to trim the domain. Same thing here. You graph the absolute value normally, but it needs to be a restricted domain from -3 to 0. So you're actually only going to graph from 0 to -3. Plug in those points, those ending points, so you can see what happens. We will practice these 2 questions in class and many others, but this is a pretty good start for you to start graphing and reviewing these graphs. You can also, from here, you can look it up here and write equations for these functions. All right? So that's a pretty good start reviewing Unit 1. Okay? This first few 10, 15, 20 questions are all about Unit 1. So good luck. Ask me for help.